Okay, welcome to the stream. I think this is about to go online. Today, basically, I just wanted to do a real quick live stream, questions and answers. I'm going to go over how to basically go from an idea to a design to an actual product, and I'm going to use the HC Control 2 that I did for my Polaris RZR. This is going to basically show you how I took a lot of different software products, mostly free or open source, KICAD, Adobe, or Fusion 360, to actually build a printed circuit board with all the components on it. I did this all in my home shop and basically come out with a really nice product that was CNC cut for the enclosure out of 6061 aluminum. If you have any questions, feel free. I've got the chat open. And I'm just going to go ahead and get started here. Okay, so this is the basic design. You kind of, it's going to be maybe hard to see here, but basically what I've got is a really small board that has a couple of ST micro silicon devices that will actually allow you to switch on and off really high loads. I designed this board. This will support about 18 amps, so it has 4 outputs. Does about 18 amps of current. No relays. It's all silent. And as far as relays are typically used on automotive stuff. The reason that you kind of see it going away in most newer cars is this can actually measure current, do soft starts, do PWM dimming, and all sorts of things that I'm sure you've seen in your car, like when you get out of your car and your dome light kind of fades out. That's what's doing that. So this is basically designed. It's 4 outputs. It does have several analog inputs and several digital inputs, as well as this actually connects to a RZR canbus. And it's looking for 2 things. Typically, well, what I've got in my RZR. I've done a couple other experimental things, but basically the 2 things it's looking for is what gear am I in, which if you have a RZR, there is no gear selection wire that you can tap onto to tell what you're on. It basically uses a resistive circuit inside the transmission and feeds that to the ECU. And what I'm doing is I'm actually grabbing that indication, what it's sending up to the dash, on the CAN bus and sending it to this. The reason I do that is because RZRs don't come with the reverse lights, and I wanted to turn my reverse lights on when I'm actually in reverse. Another thing that I did is I have a set of rock lights, and anytime that you're coming up on a section of rocks or what have you, last thing you want to do is be looking down trying to find a dash switch. Dash switches are great, but if you can have it automatically turn on, that's even better. So basically what I do is I monitor one of the analog inputs to see are my headlights on or my lights on. And if so, then once I get below a certain speed, the rock lights just automatically turn on. I do have an override on another analog input. So it allows you to do a lot of logic operations with how your devices work, which I think is really cool. And basically this is the board, and I don't know if you can see the dimensions there, but we're talking about a 1 1/4 inch wide by 3 inch board with 4 outputs and a relatively high current. The parts are actually designed for much more amperage, and you can actually spin this board with more copper and get in the upwards of 30 to 40 amps. I don't have that. I think the biggest load that I had on my RZR is about 15 amps, and that's the LED light bar. and this turns it on with no problem. Another cool thing about this particular design is you can actually bond them together. So let's say you do need more than 18 amps. You just basically use two outputs and bond them together where they're turning on at the same time. The current measuring is important. On mine, I only fuse the input onto this board. I don't fuse the outputs. Basically, the microcontroller is constantly going along and monitoring what those currents are. If they exceed whatever thresholds I have programmed in, it turns the device off. It will automatically reset after a given amount of time if you leave the device on. And you can do some really neat things. I haven't made the module yet, but more than likely I will at some point just for fun. But I'm going to make a much lower current version of this that has a lot more outputs, so that you can do things like your dash switch. When you turn on the LED light bar, let's say that you want to actually control that LED that's in the light bar switch to signal like a fault. That would allow that to happen and not eat up a really high output, a high current output. So I'm going to go through here, and basically I did all this in KICAD. I'm going to switch to the schematic here. Okay, we're in the schematic mode now. So basically there's three parts to this board. I used an STM8, which is a very inexpensive microcontroller. Not your typical Arduino. Main reasons I do use Arduino for, like, hobby projects and this, something I want to do really quick. But for something production rated, I'd recommend you go with like an ST Micro or MSP430. The STM8. I had a video on that sometime last year, I think, which basically showed my development environment. Pretty much it's just a text editor and a compiler. It's using a small device compiler. So this has three components, basically. You have your MCU and you have your FET switches, there's actually two devices, and each one of those devices has two outputs. And then you have your power section, which is a little bit specialized. I actually designed this to work on a 24-volt system as well, because I wasn't really sure where I wanted to use it, so I went ahead and did 24 volts. For those that don't know, I've been a volunteer for, 10 years, and was the chief for many of those years at a volunteer rescue squad, and they have several vehicles that are 24 volt. And I used one of these in one of those vehicles to turn on some DC loads. So I'm just going to go in here. If you're not familiar with KICAD, basically this is a hierarchical sheet. So we're going to go into this sheet, which basically is a really simple design. So here we have the microcontroller and all its components, programming header, and everything associated with this working. I did do two versions of this. For the STM8, you can get it in a normal serial configuration, or you can actually get a canbus style. They have an automotive version of this. It's canbus, and I have both. This particular one's the RS232 version. They're almost identical, other than the transceiver that you actually put on the board. Our power section, all this is really simple. This is a very simple design. I have designs based off of this that use the STM32 that are 16 outputs, which are much bigger devices. So basically what I've done, initially I started with this. I actually built this on one of the ST Micro reference boards in software first, just to make sure that I had all the software ready to go, and then I laid out all the hardware. And then, design-wise, you basically do the schematic first, and then you want to go in to do the board. I'm going to switch over to it now. And the layout on this was a little tricky. Again, we're dealing with high currents, so you have to be really careful with your layout. And there's big giant traces, a lot of calculation to make sure these would actually support the load that you're applying to the board. And then on this design, I actually did a prototype. I did a run of 3 boards at Osh Park. I really like those guys. They're really easy to work with and get your boards to you really quick. And I have a video about that as well. So what I ended up doing is actually building this board, and I didn't get it on the first try. Well, I wasn't happy with it on the first try. The board worked just fine, but the temp rise is a little too big. And what you want for temp rise is either you physically have to just measure it. A lot of times, you just use your fingers. Sometimes you end up getting burnt. The way that I did this board, just to use a FLIR camera, just to see any hot spots in the board, running it at full load, running it at over the load, to make sure that I had plenty of headroom for this to work. And then you want to take those FLIR measurements and figure out how much actual heat you're generating at a load, because that's going to tell you how much heat you have to dissipate. And that's what I used in the enclosure design. It's 60-61 aluminum. You take a look at the thermal coefficient of that material and make sure that it can wick away the amount of heat that you want to wick away. And then again, you build the enclosure, you put it in, you FLIR it. And I even, pop it open, and you want to look at and see, is this actually containing heat, or is it wicking away heat? And I ended up with something really nice. I feel very comfortable about running this at 18 amps. It basically doesn't get hot at all. I think the temp rise on it, I was measuring about 3 degrees Fahrenheit temp rise. Leaving it on for like 2 hours, which is not bad at all. And what you're looking for is a plateau. In other words, whenever you turn on the device, the heat goes up and plateaus off somewhere that's well below what your limits are. So this is basically the board. Really simple design, other than the traces. The programming header is here off the side, and then the RS-232 or 485 is on the very end, or the CAN-bus. And those are almost identical. There's a little bit of layout difference between those two, but it's very easy to do both versions without a whole lot of changes. KICAD's really nice too. After I got this laid out and produced, basically what I did is I went up and ran a 3D generation. KICAD can generate 3D information, especially if you have all your parts in 3D. And you can actually export that out and put it into Fusion 360, which we'll go on to next. And pretty much just make sure everything fits. You can get a full rendering of what the actual board and everything will look like before you ever even make it. I'm going to switch over to the Fusion 360 now. So this is our enclosure design. This is one side. It's a split box design. One of the top half just has holes, and the bottom half has threads. And basically, I'm running a cap screw through the top into the bottom, and I've got a whole series of videos on me making this and actually running this through the CNC machine. I've got a CNC mill. It's an Excel mill with family controls. And these, once I got the I was starting from scratch. I actually I had a mini mill and got rid of it and was without a mill for a long time, and finally found a replacement. And basically, this was probably one of the first projects that I actually ran on that. So, you know, I was basically learning the machine, getting the machine set up, and trying to run this new part, which took a little while, but I got it done. This is really tight fitting. The actual semiconductors on the bottom side actually touch, and then I actually have a piece of dielectric material on the other side. These particular semiconductors, they actually want to transfer the heat into the board. So what you want to do on the back side of the board, you want to have a dielectric and something contacting it to wick away heat. And this works, you know, 6061. It's not the perfect heat sink, but it works really well. There's other aluminum alloys that will have a better thermal numbers about getting heat out. But 6061 is readily available. With Fusion, I don't think that it's actually showing up, but basically the whole CAD cam is done inside of Fusion. I've got a, let's see here, 1, 2, 3, 4. I basically have 4 operations. So we've got a bottom inside, a bottom outside, the top inside, and the top outside, and those have to be done in particular order. I think the most complex one is the bottom inside. That's where I actually do all the drilling and the tapping. And I did a video on that as well. I actually use a Balix form tap, which this works awesome, especially for these really small screws. And the fit on the threads. And then once you engage maybe 2 or 3 threads, the screw actually doesn't wobble at all. There's almost no clearance. You get a really good fit. As you can see here, there's a little step inside of the enclosure. That's where the PCB fits. It almost you know, clamps onto the board, which helps with heat as well, because if any heat makes it to the edge of the board, it wicks that away. Okay. Cut back here. So overall, it was a really fun project to do. It was pretty advanced, considering that I basically did it from beginning to end. The idea, pretty complex things. We had software development, we had PCB design, we had enclosure design, and then with the exception of the actual PCB getting manufactured, I did outsource that to Oshpark. That's really not something. I do have stuff to etch boards, but not of the quality that I actually needed for this project. And double-sided boards are really difficult to do at home. Oshpark did a great job sending me the boards. I basically have my own reflow oven, have my own pick and place. I've got old Opti pick and place machine, and the first one that I built it by hand, and all the rest that I built, I've actually run a pick and place machine. And the only components that I had to do by hand were the 3-hole components. All of the machining work I basically did down in the lower shop. Got a lot of videos on that. Down there, I pretty much have everything that I need, except for I'm kind of still looking for a CNC lathe that I can fit down there. I'm kind of running out of room. But I basically did all that on the CNC mill. I did do a little bit of fixturing work for the wire placement. I did that on the grizzly mill, and that's just basically a plate that I could set on top in place of an actual top that had room for me to actually put my fingers and place all the wires before I actually assembled the top piece on. Sometimes when you solder on the pigtails, if you don't have a jig or something to actually make sure that it's going to fit, you end up with a little bit of clearance issues because you're looking for a really tight fit. And the biggest thing I forgot to mention, this is in an automotive environment and an extreme automotive environment. What I mean by that is my razor routinely sees big water holes. That's just kind of comes with the game, and it's going to get wet, muddy, and more than likely be exposed to a pressure washer. So what I did is I experimented a couple things. One was potting the entire device. That is really messy. It does work, but it wasn't really practical for even just the few that I wanted to make initially. It was going to be very difficult to do. What did work, and basically my testing, was taking a raw device, loading it, putting power on it, and putting it in a 5-gallon bucket with whatever dirt and water that I could find, and letting it run. It ended up running several days. And what I used to actually protect it is just a urethane coating over the entire board after it's assembled, after it's programmed. Everything's wired up and all the pigtails are sticking out. I would do a urethane coating. I had to go back into the Fusion 360 and add just a slight bit of clearance. The enclosure is pretty precise, so basically adding that layer of urethane on the bottom and the top. And there's several areas you have to mask off. I had to mask off the very top of the semiconductor and that kind of thing, and just add a little bit of clearance and put one together. I went to Windrock last year, I think around April, and it was really wet, and that was the testing ground. Basically, I took it up there for 4 days. I think we rode several hundred miles with no issues, and it worked great. I'm just going to check, see if anybody's joined. Okay. Well, again, this was just a test of live stream. I'm going to check the stream. I can't tell what kind of quality I'm getting, but I'll put this out. This will be a regular video, and I'm going to try to do one of these every so often, even if nobody asks any questions, just because it's a convenient format to talk about, especially like design projects and stuff like that. Because I really like the format of, I'm using OBS Studio, and it makes it really easy to flip and transition between things that are on the computer, different applications and windows. But anyway, I'm going to hang out here just for a minute, and if nobody joins, I'll go ahead and close out the video. Thanks to all the new subscribers. Just so people know, I've got a couple of messages about, errors in videos as far as like just stuff that I didn't edit out, and my response to that is I really don't spend a huge amount of time editing right now. Mainly I'm trying to do content, and basically this is stuff that I'm doing anyway. I'm not doing it particularly for YouTube, but I thought others may be interested in it. So all of this takes time, and this is just hobby and fun kind of thing. I don't want to be stuck in front of the machine editing video for hours and hours on end for a 10-minute video. So I guess that's it, and thanks for everyone subscribing, and I'll try to, again, this is just a test. The next one I'll probably actually try to put up some more notice that they're going to occur, and thanks again. We'll see you on the next one.